In this video, we're going to look at the second half of the fundamental theorem of calculus. And again, fundamental means it's really important to the whole idea of calculus. All right, so we know that an integral represents the area under the curve, and we know we can approximate this area with basically an infinite number of rectangles and a Riemann sum. All right, but there has to be a better way, and now we're going to learn finally what kind of the calculus way of doing this is. All right, so do you remember the accumulation and change formula? Hopefully, because I kind of keep mentioning it here and there. But it's a really important formula to know because it kind of helps you get between different values of your function using this area under a curve. All right, so area under a curve is useful for this accumulation to change formula. And again, just make sure we're always remembering, gonna mention it a bunch of times. All right, this prime in our definition. All right, so make sure that you always remember there's a prime in there. And with a slight alterations to this formula, that we're just going to move this over there, we get this formula. If f is continuous and differentiable, then this formula holds true. If I take the integral of the derivative from b to a, I just take f of b and subtract f of a. So it's just the accumulation of change formula, but I just move that f of a to the other side, and I get that the exact area under the derivative is f of b minus f of a. This isn't how we're normally going to see the equation, but this is the basic idea. This is just the change of the accumulation and change formula. To see the way that we're actually going to see this happen more often, are we going to need a new definition for something called an antiderivative. All right, so we'll use capital F of x for the antiderivative f. If I were to integrate f, capital F, I get to lowercase f. So we're kind of going backwards in the differentiation process. We're starting with f of x. We're going backwards to capital F. And we know this is true, that if I were to take the derivative of this, I would get f of x. So we're just trying to undo the differentiation process to get capital F. And if we switch our theorem around, before we had f prime here and the original f here and here, now we're going to put the original f here, and we have to undo the derivative process to get the antiderivative capital F. So when we're doing these exact areas, the basic process is you undo the derivative process with an antiderivative, and then you plug in the bounds. All right, so let's do an example. So we know that the derivative of g of x, x squared plus 2x, is g prime of x equals 2x plus 2. If I want to find the exact area under 2x plus 2, I undo the derivative process. So I'm going back to the original g, which we know is x squared plus 2x. And then I want to plug in some numbers. So you do this little straight line, and you put in what numbers you're going to plug in. I'm going to plug in 1 and 4. All right, so that straight line is a notation, kind of a middle step of, all right, I undid the derivative process. And now I know I want to plug in these numbers. And now the next step is I actually plug in those numbers. I plug in 4 into my antiderivative, or my original function, and I subtract when I plug in 1 into my original function. This is 16 plus 8 minus 1 plus 2. And the exact area under this curve is 21. All right, so the basic idea is I want to find the area under a curve, undo the derivative process, then plug in the top bound, subtract when you plug in the bottom bound. All right, so this is the process of the second part of the fundamental theorem of calculus. All right, so here's one for your chart on your own. We know we have this g of x function whose derivative is 3x squared minus 3. So use that in order to find the area under 3x squared minus 3. And I'll show you the answer in 3, 2, 1. And the answer you get is -2. So again, you undo the derivative process. So I go from here to here, x cubed plus 1. And I want to evaluate this at 0 and 1. So that's what that little straight line at the end means. So I plug in 1 in for x. I plug in 0 in for x. And I just simplify this expression. All right, one thing you can see is I keep these big parentheses around there because you just want to mess with that minus sign to the very end. So I simplify all this to one answer, simplify all this to one answer, and then I do the subtraction at the end. All right, so right there in those two examples we did, we kind of were given the original function and the derivative, and wanted to find the integral of the derivative. But what we're going to have to do is find these antiderivatives ourselves, and that's pretty much what the rest of this unit is about, is how do you find those antiderivatives yourself without being given them. Here's a quick summary of this video. An antiderivative is the reverse of the derivative of a function. So if you take the derivative of the antiderivative, you get back to the original. To evaluate an exact integral, you find the antiderivative and you plug in the bounds. And just one thing to be careful with, you always plug in the top bound first. So if it's something like this, you're going to plug in the 4 first and then the 1.